Hello, this is Mr. P, and today we're going to learn about the law of sines. We're going to show the typical derivation, which you find in most textbooks, and then I'll show you another one that has an additional geometric property. Let's start with the proof that you normally see in math books. We're going to start with given a triangle, ABC, so that triangle is going to have sides ABC as well. We're first going to draw a perpendicular. We're going to drop a perpendicular from C to from angle C to its opposite side, and we're going to call that H to be the height of the triangle. Now I want you to consider the right triangle on the left side here, and with this triangle we're going to look at angle A, and we're going to say that the sine of angle A is going to be opposite over hypotenuse. So sine of A is going to be H over B. And then with a little bit of algebra, we multiply both sides by B, and we get the fact that H is equal to B sine A. And you can go through that derivation each time, but eventually you'll want to come to the understanding that when you have a right triangle and you're looking at with respect to one of the acute angles, the opposite side will always be the hypotenuse times the sine of the angle, and your adjacent side will be the hypotenuse times the cosine of the angle. Sometimes it's easier to think of it in those terms. Now we're also going to look at the triangle on the right here, the other right triangle that we formed. And for this one, with respect to angle B, we're going to say the sine of B is H over A, which is opposite over hypotenuse. Or in other words, the opposite side is going to be the hypotenuse, which is A, times the sine of the angle, which is angle B. So notice how we have H being equal to two different expressions. So that means that those two expressions must be equal to each other. So setting them equal to each other, we have B sine A equals A sine B. And if we divide both sides by AB, then we get a little bit of cancellations, and it puts it in the more familiar form of sine A is to A as sine B is to B. And that shows that the proportion of or the ratio of the sine of an angle to the length of its opposite side is going to be constant throughout a triangle. All three angles will have that same ratio. And to find the one for angle C, we could simply, I'm not going to go through that part of the derivation, but if you just draw a different altitude, then you could use angle B and angle C and the exact same reasoning to find the third ratio. So all three of these ratios are going to be equal to each other. And that allows us to set up proportions so that we can solve triangles. Now, like I said, this is the typical proof that you see in a textbook, but I'm going to show you one that has an additional geometric property. So we're going to prove the law of sines again, but in a different way. This time we're going to start with a circle. We're going to be given a circle with chord AB and an inscribed angle theta. So any circle with any chord, and then we're going to draw two other chords to form an inscribed angle, and we're going to call that angle theta. Now just to finish out our diagram here, we're going to let O be the center of the circle, and we're going to let M be the midpoint of segment AB. Then my first observation is that OA and OB, if I were to draw those two segments, they would be equal to each other because they both represent a radius of the circle. So OA is equal to OB. And also, if I draw segment OM, then I should recognize that OM is the perpendicular bisector of AB. And that would be for two reasons. Number one, M is definitely the midpoint between A and B. And O, since OA is equal to OB, then O is equidistant from the endpoints of segment AB, which means the point must lie on the perpendicular bisector. So since O and M both lie on the perpendicular bisector, then the segment through them is the perpendicular bisector. My next observation has to do with these two angles that we've now created. And notice how AOB is a central angle and ACB is an inscribed angle that cuts off the same arc. So therefore the inscribed angle is 1/2 of the central angle, and OM breaks that angle up into two different equal angles, so we can see that the measure of angle theta is going to be the same as the measure of angle AOM and angle BOM. So all three of those angles have the same measure, which is theta. And now we're ready to derive our first lemma, which is we're going to look at segment AM. So we're going to consider this right triangle, AOM, and we now know that the length of the, with respect to theta, this theta, the length of the opposite side is going to be the hypotenuse times the sine of the angle. Or in other words, AM is equal to R times the sine of theta. And since AM is half of AB, then we can say that AB is just 2 times AM. So it's 2 times R sine theta. But then again, 2R, twice the radius, is the same as the diameter. So AB is also equal to the diameter times the sine of theta. And this gives us our first lemma, which is going to be that the length of a chord is equal to the diameter times the sine of the inscribed angle. And that will apply to any circle. And once you've proven that fact, then the law of sines is really just a corollary of this. So we're going to use this now to consider the following diagram. I'm going to take any triangle, and I'm going to draw the circle that circumscribes it. And any triangle can be circumscribed with a circle, if you remember your constructions from geometry. And looking at our diagram then, if I consider side A of the triangle, then that is just a chord of the circle. So side A is going to be equal to the diameter of the circle times the sine of its inscribed angle, which is angle A. In other words, A equals D sine A, using what we proved here. Likewise, if we look at side B is going to be also the diameter times the sine of its angle. So B equals D sine B. And by the same rationale, we have side C is equal to D sine C. And notice how all three of these have the diameter in them. So if we solve each of these for the diameter, then we can set all of them equal to each other, and we see that the diameter of the circumscribed circle is equal to A over sine A, which is equal to B over sine B, which is equal to C over sine C. Notice how this is the reciprocal of the way the other books usually have it. But if you use this version where the trig function is in the denominator, then it is also equal to the diameter of the circumscribed circle, which is an extra little geometric property you can use in problem solving. Alright, so we've proven the law of sine. Let's go ahead and see where it's going to be most useful. So here, a quick recap. And the law of sines is going to be used to solve triangles when you have either angle, side, angle, 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 side, or side, side, angle. So when you know those pieces of information. And the version I'm going to choose to use will be the one where it's A over sine alpha equals B over sine beta equals C over sine gamma. That's going to be the law of sine version I'm going to use. And remember that alpha, beta, and gamma are just the three angles of the triangle. So those three angles do add up to 180. And also D is the diameter of the circumscribed circle. Now, one problem that students usually have at first with law of sines and law of cosines is they're not sure when to use which one. So rather than memorize these schemes, these different congruency schemes, a much better way to think of it is if you have, because you have to have some given information in order to be able to solve the triangle, if you have the length of a side and the angle that corresponds to that side, if you have that pair of information, then you're able to use the law of sines. If you don't have that pair, then you're going to have to use the law of cosines. So when wondering which one should you use, if you have an angle and a side pair, then you can use the law of sines. Otherwise, you must use the law of cosines. All right, so let's get into some examples. Okay, first of all, that we're being asked to solve the triangle, and solving a triangle means to find all 6 pieces of information, the lengths of all 3 sides and the measure of all 3 angles. Typically, you're given 3 pieces of information, and you have to find the other 3. So here we're going to start with a diagram. You should always start your problems with making a visualization. So there, you can arrange them different ways. Here's one example of the visual, but you want to try to stay consistent. I always put side A to correspond with alpha, side B to correspond with beta, etc. And side C corresponds with gamma. So looking at our diagram here, the easiest piece of information to find would be the angle, because I know 2 angles in the triangle, so the third one is simply going to be what would add up to 180, or in other words, the 180 minus the angles that you know will give you the angle that you don't know. So 180 minus 60 minus 40 gives you 80 degrees. And remember, when you're working in degrees, you have to have the degree symbol. All right, so we know all 3 angles. We also do have a side and angle pair. Notice we have the side of 4 and the angle of 40 degrees, so we can use the law of sines. So we're going to set up a proportion. We'll solve for B. Will be the first one we'll solve for. So we're going to say B is to the sine of its angle, as 4 is to the sine of 40. So this is the proportion we set up. B is to sine 60, as 4 is to sine 40. Now, solving this equation for B, we're going to multiply both sides by sine 60, and we get B is equal to 4 sine 60 over sine 40. Now, for a common trap I want you to avoid is you should not put in sine 40 into your calculator, get a decimal, write it down, put in sine 60, get the number, write it down, and then start doing the multiplication. Because you never want to round in the middle of a problem. Whenever you round, you introduce error, and then if you do operations to that, you're going to multiply that error or exponentiate that error, and it can affect a significant digit. So the habit to get into here is always manipulate it so you get an exact answer. This is the exact answer. And then you put that expression into the calculator and get your approximate answer, which is 5.39. So B is approximately 5.39, and make sure you distinguish between approximately equal and exactly equal to. All right, so we know B, we know gamma. The only thing left is to find length C. So again, we're going to set up the law of sines. We have C is to the, we also do know gamma, so we have C is going to be to the sine of 80 degrees. Now for the other one, now that we do know what the length of B is, we could use the pair of B and 60 degrees, or we could use the 4 and 40 degrees. And for the same reason why we didn't want to plug this into the calculator earlier, is you want to make a smarter choice. You do not want to use this value in your next calculation because this is a rounded value. So when you set up your proportion, you definitely want to use the 4 and 40 degrees because those are exact values. So C is to sine 80 as 4 is to sine 40. And again, if we solve for C, we're multiplying both sides by sine of 80. And you get C equals 4 sine 80 over sine 40. Put that in the calculator, and you get approximately 6.13. So it's very important to develop the habit of not rounding in the middle of a problem. Work the problem out algebraically, and then put the expression in the calculator once at the end to get your answer. Okay, let's look at the one hiccup with the law of sines is when you get to what we call the ambiguous case. And you notice how it had the side-side angle, which is not actually a congruency scheme, but in certain circumstances we can still solve the triangles. So here with side-side angle, and here's an example of if I know this side, and I know this side, and I know this angle, then it's a little ambiguous because I could have a couple of different situations. Depending on, I don't know what the length of this side is, and I don't know what this angle is. So even though I know this side, I don't quite know what angle it's at. And it's possible to not even have a triangle at all. So it's possible to have no solution. For example, if we look at the height from this point to this line, now as I'm looking at this distance here, and if I were to actually draw that as a perpendicular distance, then this would form a right triangle, so that height would simply be the hypotenuse times the sine of the angle. In other words, if I call this h, then h would equal b sine alpha. Now, the thinking I want to go on here is that if this side is not longer than h, in other words, if a is less than h, then it does not matter what angle this is at, it will never reach down here to create a triangle. So if it's smaller than h, then it's simply no solution. And now if it's equal to h, you see that we can make a triangle, and if it's longer than h, it's possible to make a couple of triangles. But to run you through all of the logic, let me first give you your little chart here, and then I'll walk you through these. So first of all, if a is less than h, then as we can see clearly there's going to be no solution. Now if a is equal to h, if it's exactly equal to h, then there's going to be exactly one solution if your alpha, if this angle is acute. So this would be exactly one solution, and it would be a right triangle. And if you look at if alpha is obtuse, then by this visualization, a could equal h, which it does here, but notice how if I swing it over, I still can't make a triangle with it. So if a is equal to h, you do have a solution if alpha is acute, but if alpha is obtuse, then you still have no solution. Now if a is greater than h, then this is the one you have to be careful of, because you could have one, two, or no solutions. So first of all, we're going to look at the what happens when it's acute. If it's acute, then if it's longer than the height, but still less than the length b, then we could swing this way, and that would be a triangle, or we could swing it this way, and that would be a triangle. So you'd have two possible triangles here. However, if it gets so long that it's longer than side B, when you swing it over to this side, if it swings past that vertex, then notice how you still can't make a triangle on this side. If you swing to the other side, you can still make a triangle. But swinging this way, it swings past that vertex, and you have no triangle. So if A is greater than B, then you're only going to have one solution on this side, no solution on the other side. And then the other option is if we have our obtuse triangle, and A is longer than the H, but still not longer than B, then as we swing over here, we're still not going to be able to make the triangle. As we can see in the obtuse case, the only possibility of having a triangle is if A is longer than B, and that way it can come over here and make a triangle. So therefore, these are the three possibilities. A is less than H, A is equal to H, or A is greater than H. And when A is greater than H, you're going to have if alpha is, well, I don't have the alpha in there, but if alpha is acute, then there is only one solution if A is greater than B, and two solutions otherwise. And if alpha is obtuse, then there's only one solution if A is greater than B, and no solutions otherwise. Because for both of them, you do have to compare it to the height, which is the distance from that point to the base. Alright, so let's look at an example of this. Here we want to solve this triangle. We have A, B, and alpha. So if we think of our first step is always to draw that visualization. So here's an example of drawing this triangle. We know the angle, and we know the length of the side over here is going to be 6. We just don't know at what angle it goes. And the side between this side here was going to be 8. So when we set up our 6, the first thing we need to know is it long enough to make a triangle in the first place? So in your ambiguous case, you first want to calculate h, which we said was b sine alpha. So b is 8, alpha is 35, so 8 sine 35 gives us approximately 4.6. Well, 6 is longer than 4.6. The distance from C to this line is 4.6, and A is longer than that, plus A is shorter than this side here. So it's in that sweet spot where we're going to get two possibilities, and this is what they would look like. Either the 6 goes this way to create this triangle, or it goes this way to create this triangle. So we need to know point B could be over here, or point B could be over here. And both of these would satisfy these three conditions. So when we have the ambiguous case and two solutions, we do have to solve for both of them. So let's solve for the acute angle first. That's usually the easier one because the calculator gives you acute angles. So we're now considering the big triangle here. We're going to set up the proportion that 6 is to the sine of its angle, as 8 is to the sine of its angle, which is beta. So 6 is a sine 35, as 8 is a sine beta. A little bit of algebra, we cross multiply, divide by 6. You're going to get sine beta is equal to 8 sine 35 over 6. And that is an exact value. However, we don't want sine beta. We want to know what is beta, what is the angle. So if we take the arc sine of both sides, the arc sine of the sine just gives us beta. And then on the right, we get the arc sine of that expression. And at this point, you don't have to draw a triangle for this. You don't have to work this out by hand. You can simply put this expression into the calculator, as long as you put it in there properly. Then you will get that beta is approximately 49.9 degrees. Make sure your calculator is in degree mode. Otherwise, you will get a different answer. Now, if you remember from earlier, the calculator only gives you the answer that's within the restricted domain. So it only gives you one of these two possible answers. So to find the second answer, the rule for sine is once you know your first answer, your second answer will be pi minus that first answer if you're dealing in radians, or 180 minus that first answer if you're dealing in degrees. And here we're in degrees, so 180 minus 49.9 gives us our other angle, which is 130.1. So in the ambiguous case, it's possible to have two answers. It's also possible to have no answers, or it's possible to have one answer. So make sure you draw your diagram accurately so that you can figure out which case you have. All right, let's look at an application of this for word problems. For surveying and for measuring distances, trigonometry is used a lot. And with this problem, we're looking at trying to find the height of a mountain. So to measure the height of a mountain, a surveyor takes two sightings of the peak, and one is going to be at a distance 900 meters from the first measurement. So we can see the resulting elevations. When the surveyor is standing here, his measurement is 35 degrees to the peak. When he gets 900 meters closer, his elevation is 47 degrees to the peak. And the question is, what is the height of the mountain? And they want us to round to the nearest meter. And the height of the transit is 2 meters off of the ground, by the way. All right, so our first step is always to draw a visualization. Now they give us a chart here, or they give us a picture, but we want to make a diagram that we can add to and start solving for pieces of the puzzle. So we're going to create our own diagram. We're taking their picture and making it more theoretical. And we're going to label the parts that we're looking for. So we're going to call the 900 meter side of this scalene triangle, we're going to call that alpha. We're going to call that A, so alpha will be the angle opposite it. We're going to call this angle gamma, so C is the side opposite that. And we're going to use B to represent the distance from the top of the transit to the top of the mountain. Alright, so looking in the diagram here, the easiest thing to solve for right away would be the angle gamma, because notice we have the 47-degree angle here, plus whatever gamma is makes a straight line. So in other words, gamma is 180 minus 47, which is 133 degrees. Now for alpha, you could use gamma plus the 35 degrees plus alpha would equal 180. Or there's an even quicker and easier way is to notice that the 47-degree angle represents an exterior angle. And if you remember from geometry, the sum of the two remote interior angles is equal to the exterior angle. So in other words, alpha is simply going to be 47 minus the 35, which is 12 degrees. So you'll find that geometrically there's usually more than one way to arrive at these values. Alright, so now we're ready to write a proportion. Notice how, now that we know alpha, we have an angle and a side pair, so we can use the law of sines. So in order to find side C, we're going to say that C is to the sine of its angle, which we now know to be 133, as 900 is to the sine of alpha, which we now know to be 12. So C is to sine 133, as 900 is to sine 12. And this implies that C is equal to 900 sine 133 over sine 12. In other words, I just multiply both sides by sine 133. Now this is an exact value. This is not what we're ultimately looking for. So we don't want to put that into the calculator and get a decimal, because that would be introducing error in the middle of the problem. So we're going to keep that as an exact value and continue on trying to find the value for B. So for B, we're going to use the fact that now we're considering the large right triangle. So with regard to the 35-degree angle, with respect to this angle, B is the opposite side. So in other words, the sine of 35 is equal to B over C. And of course, this implies that B equals C sine 35, or in other words, with regard to the 35-degree angle, the opposite side is the hypotenuse times the sine of the angle. Now we already know an exact value for C, which is this expression. So if we substitute that in for C, we'll get that B is equal to all of this times sine of 35. So this is our actual exact expression for B. Now we have something we can put into the calculator once, and when we do that, we get that it is approximately equal to 1,815.86. And now this is where you do have to be careful, though, because when solving problems, especially word problems, your first step is to make a visualization. However, your last step is to always make sure you're answering the question being asked. Notice how we figured out the length of B, but that's not actually what the question is asking. They want to know what is H, the height of the mountain. Notice here how H is B plus that 2-meter transit. So we still need to add 2 meters to this, and then we also need to follow directions by rounding to the nearest meter. So H is really B plus 2, which is going to be approximately 1,818 meters. And we're done.